Yeah. So today we'll discuss nanotechnology in display devices. Okay. So what are display devices? Most of you are engineers. You know what are display devices. I don't have to discuss mostly about what is display device. That you can tell it to me. Okay. But I'll tell you how nanotechnology is used in display devices. Okay. So you might have seen this. Okay. Next generation, your cell phones will be like a paper. Just fold it and keep it in your pocket. Okay. QLED or OLED it is. Okay. You can see that guy is holding, right? It's flexible. Display devices are very flexible. Okay. Transparent screens. You can see through the other side. Okay. This is a QLED or OLED. Transparent screens, which are now commercialized already. Okay. Not in India, but outside they are available. Okay. See, this is wallpaper screen. Okay, TV. Okay, that guy is holding the wallpaper TV. Okay, you can fix wallpaper TV on any walls. Just you roll it and just bring it and fix it in somewhere. Just so like a wallpaper. That's it. Right. It's both side screens. Other side somebody is using, and this side is also a double-sided display device. It is. It's also made up of OLED or QLEDs. Okay. So got it. It's very interesting. Display devices, electronics. I think electronic students know it already. But anyway, so QLEDs and all, they're all nanotechnology. So what are they? Okay, nanotechnology in displays. Okay, display technologies can be grouped into three broad technology areas. Okay, one is organic LEDs, OLEDs we say, and QLEDs. Organic chemistry got importance because of OLEDs. Okay, they are used as LEDs. Organic compounds are people started using in light emitting devices. See, can anyone tells me can we use silicon in LEDs? It's a semiconductor, right? Can we use silicon in LEDs? Yes or no? You may be wrong. Just if you know, you tell. Otherwise, say I don't. We don't know. Can we use silicon in LEDs? Yes or no? Yes or no? Can you hear me? Okay. So I don't want to interact with this one. Then it's a big problem for me.
No,
Anyway,
sir, I guess.
uh, you cannot use. Why?
Sir, it produces heat.
Nothing to do with heat. When it is excited, electron will not come back to the same state. Okay, when it is excited electronically, okay, it's a semiconductor, right? So when it is pumped to the higher energy levels, okay, electronic levels. So what happens? It goes into the circuit. It will not come back. Okay, means the basic requirement of an LED, any right semiconductor, it should have direct band gap, not indirect band gap. Silicon has got indirect band gap. So indirect band gap means when it is excited, it will not come to the same state. Okay, it goes to that state and the electron goes away. It will not come back. Okay, in LEDs it has to come back. For example, gallium nitride can be used. Gallium nitride is a direct band gap semiconductor. When it is excited, it comes back to the ground state, emitting a photon. Okay, so LEDs we require direct band gap semiconductors. Is it clear to you? Indirect band gap semiconductors are used in solar cells, where you use that electron to generate electricity there. Okay, light energy is converted to electrical energy. Okay, but here in LEDs, electrical energy is converted into light energy. Other way around. Do you agree with me?
Yes, sir.
Okay. Yes. So you can excite an electron from valence band to conduction band and generate, produce light. We call it as electroluminescent. LEDs are electroluminescent. They have what? Right, luminescent property because of you're supplying electricity, voltage, right? So organic LEDs, they work in the similar line. We call them right, instead of conduction band and valence band, we call in organic chemistry they call it as HOMO and LUMO, highest occupied molecular orbitals, okay, and lowest unoccupied molecular orbitals. Okay, HOMO to LUMO transition. Okay, they call it as. Okay, so they are also semiconductors. QLEDs, quantum LEDs. Here we use quantum dots, nanoparticles, semiconducting nanoparticles. Okay, next is electronic paper. Okay, it's kind of normal paper you use. Okay, so you can write, you can just read. Kindle, they use electronic papers. Okay, they also use OLEDs, Kindle, Amazon Kindle. Okay, QLEDs. Okay, other devices intended to show still images and field emission displays. Okay, field emission displays are similar to your CRTs. I think electronic and electrical people might have studied this. Okay, field emission displays. Okay, FEDs we say. Right. Anyway, nanotechnology in displays are categorized into three categories: organic LEDs or QLEDs, electronic paper, and other devices intended to show still images, and FEDs, field emission. Okay, organic light emitting diodes. The first light emitting diode. Okay, it's not called OLED, it's called POLED. It's polymer. Okay, synthesized by J.H. Burroughs et al. Okay, which involved a single layer of polyparaffin vinylene. Okay, it's a polymer which is used as electroluminescent layer. Okay, electroluminescent layer in OLEDs. Okay, another is there, ALQ3 is there, which is common component in organic light emitting diodes. Okay, it's a complex compound. Okay, tris 8 hydroxy quinolinato aluminium. Okay, don't have to remember that. I just mentioned ALQ3. Okay, commercially it is known as ALQ3. Is a common component of organic light emitting diodes. So variation in the substituents on the quinoline group rings affect the luminescent properties. Okay, you can get different colors. Okay, by modifying the structure. Okay, that's how it works. Okay. So organic light emitting diodes, how it is constructed, okay, and how it works. Okay, a typical OLED, okay, organic light emitting diode composed of a layer of organic materials situated between two electrodes. Okay, you can see here two electrodes, two electrodes. This is cathode, and the bottom one is anode. This is cathode and this is anode. Okay, in between we have conducting layers. Okay, OLED. Okay, it's a schematic of a bilayer OLED. Okay, so this is cathode. The second one is emissive layer. This is called emissive layer. Okay, emissive layer. Okay, this is emission of radiation. I can show it as this is third one. This is emissive layer. This is any conducting material. Okay, cathode. Okay, and this is photoconductive layer. Okay, this is fourth one, and here it is anode. Fifth one is anode. So this is the common, right, architecture of OLED. Okay, the organic molecules are electrically conductive as a result of delocalization of pi electrons caused by conjugation over a part of the molecules. Okay, you can see this conjugation. Conjugation means double bonds. Okay, double bonds are made up of two electrons, right? Okay, one, if you remove one electron, this electron is delocalized. Okay, it can move anywhere, so thus it becomes conducting. You can remove one electron from here, it becomes conducting. Okay, these pi electrons, actually there are two electrons here. Okay, we show the double bond. Actually, we have two electrons to form a bond, pi bond. Okay, if you remove one electron, so if one electron is left, so that will be delocalized everywhere. It can move anywhere. So delocalization means it moves. Okay, so because of that, pi electrons, right, conservation over this is electrolytically conductive. These materials have conductivity levels ranging from insulator to conductors. They are basically semiconductors. They are called organic semiconductors. So highest occupied molecular orbitals and lowest occupied molecular orbitals. HOMO means highest occupied molecular orbital and lowest unoccupied molecular orbital. Okay, semiconductors are analogs to this. Is HOMO means highest occupied molecular orbital, means it has got electrons, so it's called valence band. Conduction band. Okay, when this electrons present in valence band are pumped to conduction band, it becomes conducting. Okay, so like commercially known, right, semiconductors, inorganic semiconductors like TiO2, silicon, and all, they're all they have got valence band which is rich in electrons, conduction band, okay, which the electrons are pumped to the conduction band, okay, using light energy or electrical energy, whatever it is. Okay, so if you use electrical energy, you can use it as a LED. If you use light energy, you can convert it to electrical energy. Okay, but what kind of semiconductors they show this solar right property, solar cell property, okay, photovoltaic properties. They are indirect band gap semiconductors. Direct band gap semiconductors show what? LEDs. Okay, right, light emitting diodes. So materials usually I told commonly anode. Anode I mentioned. What we use anode? It's usually indium doped tin oxide. Okay, conducting glass we use. Okay, we use conducting glass here. Okay, then it's a transparent to visible light and has high work function, of course, which promotes injection of holes into the HOMO level. Okay, and of the organic layer. The second conductive layer, injection layer, is typically added, which may consist of P dot and all. This is a right polymeric compound. You don't have to remember all these things, right? So basically, we use metals such as barium and calcium. They are used as cathodic materials. Okay, here cathodic materials are barium or calcium. Okay, these are very active materials, right? So that's the reason you require capping layer. Okay, they are encapsulated with, they are covered with aluminum, because otherwise they are very reactive. Calcium and barium are reactive metals. Okay, so one important, right, two secondary benefits of aluminum capping is you can have robustness in electrical contacts, and the back reflection of emitted light out of transparent layer can be achieved. Okay. Similar to OLEDs, we have QLEDs, quantum dots. You know what are quantum dots? Semiconducting nanoparticles whose whose diameter is of the order of Bose exciton radius. Okay, because they are both photoactive. Okay, quantum dots are photoactive, means photoluminescent. We have discussed in the optical properties of nanoparticles, and electroactive. Okay, they have got electroluminescent property. If you supply electricity, they'll give the photons. Okay, luminescence. Okay, and have unique physical properties and are one of the most promising optoelectronic materials. Okay, optoelectronics, you know, it's a part of electronics, where we talk about these things. Okay, photonics, part of photonics. Okay, will be at the core of next generation displays. Okay, so compared to organic luminescent materials in OLEDs, okay, so QLEDs, what is the advantage? You know, organic compounds can be easily decomposed, right? If you supply more electricity and all, they start decomposing. But inorganic compounds like titanium dioxide and other things, they will not easily decompose. Okay, that's the reason quantum dot QLEDs are purer in colors, longer lifetime because they cannot be easily degraded, and lower manufacturing cost, and lower power consumption. Another key advantage is quantum dot displays. Uh, right, key advantage of quantum dot is that because of QDs can be deposited virtually on anything, okay, any substrate, you can expect printable and flexible, even rollable displays of all sizes. Okay, even OLEDs also you can deposit, but OLEDs, the problem is they may decompose, they may undergo thermal degradation, or they may undergo, photo degradation. That's another problem. But QLEDs are not like that. They will not undergo degradation easily because they are inorganic compounds. Metal oxides, okay, they are very stable. TiO2 is very stable. For instance, for instance, researchers have demonstrated passive matrix quantum dot LED QLED display fully integrated with flexible electrons. I had shown you in the first pictures. Okay, they have shown many QLEDs are available in the market. Okay, even in India also QLED TVs are available, but not rollable yet, not rollable, not transparent yet. Okay, they will also come in 1 or 2 years, not not long. Okay. Then we go to electronic papers. Okay, e-papers we say electronic paper. Okay, they are very simple. Right, right. You require one transparent electrode. Okay, layer. Okay, maybe it's made up of ITO or something. Okay, you require what liquid polymer layer containing uh, e-ink, ink we say. Okay, that's a capsule. Okay, there here, and lower electrode, another electrode there. Okay, then you need to supply voltage, right? Appearance of pixels can be seen. Okay, so you can get the pixels here. Okay, so these are commercially available. Electronic papers are available. Unlike conventional flat panel display, which uses power consumption, consuming the backlight is required for many right LCDs and all. Okay, to illuminate its pixels, electronic paper reflects light like ordinary paper. It reflects like ordinary paper and is capable of holding text and images indefinitely without drawing electricity. See, any and while allowing the image to change later, can be changed later because they can be produced on a thin, flexible substrates, and due to their paper-like appearance, okay, usually electrophoretic displays, they are all okay. I'll discuss this bit. Electrophoretic. What is electrophoretic? And are considered prime examples of electronic paper category. Okay, electrophoretic displays already are in commercial use. They are already there. Okay, your Kindle, Amazon Kindle, and Sony Reader, they are there. But mostly they are black and white. Okay, because there are but colors are very costly. Okay, quality issues with the color displays. Electronic papers. Okay, mostly we are talking about black and white displays. Okay, nanotechnology researchers have shown that organic ink nanoparticles could provide an improved electron ink fabrication technology, resulting in e-paper with high brightness, good contrast ratio, low manufacturing cost. So that's the advantage of. People can use micro particles also for electronic paper. Okay, nanoparticles gives you better brightness, good contrast ratios. Okay, so electronic paper, one technology is called Garicom. Right, what is this technology? It consisted of it's long back. Okay, it's not new. Okay, long back they have developed this technology. It consists of polyethylene spheres. Okay, polyethylene, you can develop this easily. Okay, polyethylene is your polythene bags. Okay, just make them spheres. Okay, they can melt. Okay, they are all thermoplastics. Okay, so just you have to create 75 to 100 micrometer sizes. Okay, each sphere is a genus particle. Okay, genus means uh, it has got in one particle there are two properties. Those kind of particles are called genus particles, composed of negatively charged plastic on one side and a positively charged white plastic on the other side. Means each bead has got, for example, one bead is there. Okay, okay, one microsphere is there. So part of it, for example, I say A, this A, okay, and this part is B. The same particle, it has got two different physical properties. Okay, genus means two different physical properties. One side is negatively charged, another side is positively charged. So we call it as a dipole. Okay, dipole. Okay, one side it is coated with black, other side it is coated with white. Okay, so if you apply, for example, a positive charge you apply here, okay, what happens? It turns, right? It turns like this. Okay, negative A side will appear here. Is it clear to you? So it becomes what? White. Okay, if you apply negative charge here, it becomes black. So you can arrange them in a regular pattern, so so that you can write something. This is simple technology. Okay, the spheres are embedded in a transparent silicon sheet. Okay, silicon sheet with each sphere suspended in a bubble of oil, so that it can rotate freely. So it should rotate, right? Whenever you apply some voltage, for example, I have applied voltage like this. Okay. So in this part, I have applied what? Negative charge. Okay. So what will the display look like if I apply negative side on this side? Okay. If I apply negative side, negative voltage in this side and positive voltage on the other side, back side, what I can see? Tell me whether it is white or black. E, whatever I have written. Just think it over. I have applied on the front side negative charge. So what happens? Positive charge, white particles, white plastic particle will rotate like this. Okay. So positive charge will come on the top. Okay. Negative charge go on behind. Right. So if I read from the top, it looks like E is written in with white ink. Okay. If I change the polarity, I'll make it positive and I'll make the bottom negative. Now E will be written in with blank ink. Okay, because when I apply positive charge here, so negative charge will right automatically move this side because of attraction. You got it? This is called Garicon. Okay, so they are free to move because of this. They are suspended in oil. Okay, uh, right. So another paper technology is electrophoretic. So in the simplest implementation of electrophoretic display, TiO2, for example, titanium dioxide nanoparticles are approximately 1 micrometer diameter is dispersed in hydrocarbon oil. Okay, nowadays people are using it in nanometer scale. Okay, earlier it was 1 micrometer. Now we can go for up to nanometer scale. So dark colored dye is added. What we do? We add a dark colored dye. Okay, these nanoparticles, TiO2 nanoparticles are white in color, right? So it's kind of white ink. Okay, and you are adding dye color, right? What is that? Dark colored dye in oil along with surfactant. Surfactant just to it helps in the rotating of spheres. Okay, charging agents. Okay, cause the particle to take an electric charge. Okay, so a different you can go for different pH values. Okay, at high pH value, TiO2 is negatively charged. Okay, so like that they do. Okay, this mixture is placed between two parallel conductive plates separated by a gap of say 10 to 100 micrometers. When voltage is applied across the two plates, okay, the particles migrate electrophoretically to the plate that bears opposite charge from that one on the particles. The same, okay, like Garicon, it's electrophoretic. Okay, when particles are located at the front side of the display, it appears white because the light is scattered back to the viewer, okay, by the high index. That's what you call that titanium nanoparticles. Okay, when the nanoparticles are located at the rear side of the display, it appears dark because incident light is absorbed by the colored dye. If the rear electrode is divided into number of small picture elements, the pixels, then an image can be formed by applying appropriate voltage to each region of display, okay, to create a pattern of reflecting and absorbing regions, so that you can generate, okay, you can type any material, okay, any letter, okay, image. Here is one more technology, micro encapsulated electrophoretic display. In the same electrophoretic display, okay, electrophoretic display forms images by rearranging charged pigment particles, right, with an applied electric field. So this uses tiny microcapsules filled with electrically charged white particles suspended in a colored oil. Okay. So one more technology is there, electrowetting. Okay. What is electrowetting display? It is also based on controlling the shape of a confined water oil interface by an applied voltage. Okay, with no voltage applied, the colored oil forms a flat film. Okay, between the water and the hydrophobic, water repellent insulating coating on an electrode, resulting in a colored pixel. Okay, when voltage is applied, the electrode and the water, the interfacial tension between the water and the coating changes. So as a result, the stacked state no longer stable, so causing water to move the oil aside. Okay, so you will get this makes a partly transparent pixel. If a reflective white surface is under the switchable element, a white pixel appears. Because of small pixel size, the user only experiences the average reflection, which provides a high brightness, high contrast, and switchable element. One more is that electrofluidic. Electrofluidic display is a variation of electrowetting display, the same whatever we discussed. Electrofluidic display displays place an aqueous pigment dispersed inside a tiny reservoir. Okay, so earlier you used oil pigment. Okay, here you are using aqueous pigment. That's it. The reservoir comprises of 5 to 10% of viewable pixel area. Okay, therefore the pigment is substantially hidden from the view. Okay, voltage is used like to electromechanically pull the pigment out of the reservoir and spread it as a film, okay, directly behind the viewing substrate. As a result, display takes on color and brightness similar to that of conventional pigment printed on a paper. Okay, when voltage is removed, okay, liquid surface tension causes the pigment dispersion to rapidly recoil into the reservoir. So technology can potentially provide 85% of wide state reflectance for electronic paper. So there's one more technology, interferometric modulator. Okay, Mirasol they call. The technology used in electronic visual displays that can create various colors by interference of light, reflected light. Interference, you studied in PUC, right? Interference, diffraction, and polarization you have studied. Okay. So the color is selected with an electrically switched light modulator comprising a microscopic cavity that is switched on and off using driver integrated circuits. Okay, similar to those used to address liquid crystal displays, LCDs. I think some of you might have studied, okay, electrical and electronic students. Others, LCDs, okay, maybe in PUC level you might have polysteryl benzoate. Uh, Researchers have turned to carbon nanotubes now, field emission displays. Okay, they are similar to your CRTs. Okay, cathode ray tubes. Okay, so only thing here, you are using field emission displays. Okay, you are using carbon nanotubes to create new class of large area, high resolution, low cost, flat panel displays. Some believe that field emission display technology utilizing carbon nanotubes as electron emitter. There, what you used to do in CRTs, cathodes used to be heated to emit electrons. You don't have to heat here. Okay, you don't have to be heated. Okay, cathodes. Okay, so at cold temperature, okay, the CNTs emit electrons. Okay, so FED is the technology of choice for ultra high definition widescreen televisions. Okay, field emission displays. FEDs, in sense, are hybrid of CRT televisions. Okay, cathode ray tube televisions and LCD televisions. Okay, nowadays we are not using CRT and LCDs. Okay, they capitalize on the well-established cathode anode phosphor technology. Same technology, cathode anode phosphor technology, built into full-sized CRTs. Using this combination with the dot matrix cellular construction of LCDs. Okay, the electron emitter arranged in a grid are individually controlled by cold cathodes. As I mentioned, they are all cold cathodes because you don't require to heat nanotubes at a high temperature to emit electrons. Okay, unlike in normal CRTs, field emission does not rely on heating the cathode to boil off electrons to generate colored light. Alright, field emission display technology makes possible the thin panel of today's liquid crystal displays offers a wide field of view. Okay, provides high image quality of today's cathode ray tubes displays and requires less power than CRTs. Okay, I think I'll stop here. Right. If you have any questions on this, you can ask me. Or right, notes and all, I'll share it with you. Okay, and also you whatever the seminar you have given, you share it in the group. Okay, in the WhatsApp group. Okay, or whatever the PPTs you prepared, incorporating whatever the suggestions I have made. Okay, I have given you. Okay, any questions? No questions?
No, sir.
Okay. So in the next class, what I'll discuss is synthesis of that hydrothermal method. Okay, and some whatever I have missed. Okay, labs I would have conducted. Okay, I think I have discussed silver nanoparticle synthesis in the class earlier. If not, I'll cover it anyway. Okay, this will be my 31st class, right? 31st or 32nd class. Okay, in that we have covered 3 days of seminars. Okay, and one more person is going to give seminar on. I think one person is left. Who's that? Sachin. Sachin has not given the seminar, so he wants to give the seminar on next Tuesday. Okay. After that, we don't meet regularly. We don't have to meet regularly because I have covered all the syllabus. Okay, and I'll share the notes. Okay, we just meet for 10-15 minutes and we'll discuss whatever any doubts and any difficulty. Okay, and I'll share all the notes and everything. Okay, if you have questions, you can discuss during that time. Okay, um, is that fine with you?
Yes,
Yes.
sir.
Okay, okay then. We'll stop here. And we'll think we'll take it up in the next class.